Welcome back to Basic Electronics. We looked at a simple diode circuit in the last class. We will now look at a similar problem, but with two diodes. We will first obtain the VO versus VI relationship for that circuit, and then use it to plot the output voltage as a function of time for a specific input voltage waveform. So let us start. Here is our next example, and it is a little more complicated than the previous example because we have two diodes now, D1 and D2, and we want to plot VO, this voltage here, as a function of VI, this voltage, with VI in the range minus 5 volts to plus 5 volts. And once we do that, we want to plot VO as a function of time for a triangular input going from minus 5 volts to plus 5 volts with a frequency of 500 Hertz. And the diode model that we want to use is the same as the one that we used in the previous example. That is, if the diode conducts, then the voltage across the diode is constant, 0.7 volts, and if the voltage is less than 0.7 volts, then the diode does not conduct. Alright. Now this example does look more complicated than the previous one, but let us show that if D1 is conducting, then D2 cannot be conducting, and vice versa. And once we show this, then the whole problem becomes much simpler. Let us suppose that the diode D1 is conducting. In that case, as we go from A to B, we have a voltage drop of 0.7 volts here across D1, then this voltage drop of 1 volt, and after that we have a positive voltage drop across R1, because this current I1 can only be positive since the diode can only conduct in that direction. So the voltage difference between A and B, that is VA minus VB or VAB, must be greater than 0.7 plus 1, that is 1.7 volts, because this voltage drop can only be positive. Okay, so what it means is that for D1 to conduct, we must have VAB greater than 1.7 volts. Let us now take the next case, that is D2 is conducting. If D2 is conducting, we have a voltage drop of 0.7 volts in that direction, and also we have a positive voltage drop across R2 in that direction, because this current I2 can only be positive since D2 can conduct only in that direction. So what it means is VB minus VA must be greater than 0.7 volts now, because this voltage drop I2 R2 can only be positive. In other words, for D2 to conduct, we require VBA to be greater than 0.7 volts, and what that means is VAB must be less than minus 0.7 volts. So we require VAB to be greater than 1.7 for D1 to conduct, and we require VAB to be less than minus 0.7 for D2 to conduct. And clearly these two requirements are contradictory, so therefore we can have either D1 conducting or D2 conducting. The arguments that we just presented are summarized over here, and the conclusion is that if D1 is on, then D2 must be off, and if D2 is on, then D1 must be off. Let us now look at these cases one by one. Here is the case where D1 is conducting and D2 is not conducting, and then the current path is like that. And in this situation, the input voltage VI is given by KVL. It is equal to this voltage drop plus 0.7 plus 1 plus this voltage drop across R1. Now this voltage drop across R is R times I1, because this same I1 is flowing through R as well. So we have I1 times R plus 1.7 plus I1 times R1. So that is our VI. And what it means is that VI must be greater than 1.7 volts, because this term can only be positive, because the diode can only conduct in that direction. So therefore I1 must be positive. Here is our second case. in which D2 is conducting but D1 is not conducting. And let us obtain Vi in this case by writing the KVL for this loop. Okay, let us start from this point. We go down like that, come across a voltage drop of Vi, so that we take as plus Vi. Then we come across a voltage drop of R2 times I2, then a voltage drop of 0.7 across D2, and then a voltage drop of R times I2 across R. So these voltage drops when added must give us 0, and that is this equation here. So that gives us Vi, that is minus 0.7 plus I2 times R plus R2. Let us look at this number in the brackets here. It's 0.7 plus I2 times R plus R2. Now I2 can only be positive because D2 can only conduct in that direction, and therefore this number is always larger than 0.7 volts. So what it means is Vi must be less than minus 0.7 volts for D2 to conduct. So we have Vi greater than 1.7 volts when D1 conducts, and Vi less than minus 0.7 volts when D2 conducts. And in between these two limits, that is for minus 0.7 volts less than Vi less than 1.7 volts, neither D1 nor D2 can conduct. Alright, we know a lot of things about the problem now, and let us proceed to obtain Vo as a function of Vi. Let us start with this situation, that is Vi between minus 0.7 volts and 1.7 volts. And as we saw in the last slide, for this case both D1 and D2 are off. So that means there is no current in this branch, no current in this branch. So therefore there is no possibility of any current through R. So what it means is this output voltage Vo must then be equal to Vi, because there is no voltage drop over here, like that. Here is a plot of Vo versus Vi, and the situation that we just discussed is right here, Vi between minus 0.7 and 1.7, and the Vo versus Vi relationship in this region is given by this straight line over here, which is represented by Vo equal to Vi. So this is a straight line with slope equal to 1 and passing through the origin, like that. And in this situation D1 is off and D2 is also off. Next, let us take Vi less than minus 0.7 volts, and for this range, as we saw in the last slide, D2 conducts, D1 does not conduct. And what is the output voltage in that case? Let us start with this voltage drop, Vb minus Va. So that is I2 R2 plus 0.7. And what is Vo? Vo is just negative of that. So Vo is minus 0.7 minus I2 R2. Let us now find this current I2, and we will do that by writing the KVL equation for this loop here. Let us start at this point. We go down first, come across a voltage drop of Vi, so we take that as plus Vi. Then we come across a voltage drop of I2 R2, then a voltage drop of 0.7, and then a voltage drop of R times I2. And these voltage drops must add up to 0, and that is this equation here. Now from this equation we can obtain I2. I2 turns out to be minus Vi plus 0.7 divided by R plus R2. Let us substitute this I2 now in this equation for Vo, and that gives us Vo equal to R2 by R plus R2 times Vi minus 0.7 times R by R plus R2. The slope dVo dVi is given by this factor here. R2 is 0.5k, R is 1k, so therefore the slope turns out to be 1 over 3. Let us look at the plot now. We are talking about Vi less than minus 0.7 volts, this region here. D2 is on, D1 is off, and we have a straight line describing VO versus Vi, and that line has a slope of 1 over 3. Note that the VO versus Vi relationship is continuous as we go from this region to this region, and that can be seen also from equation 2 here. At Vi equal to minus 0.7 volts, equation 1 predicts that VO should be minus 0.7 volts, and let us see what equation 2 predicts. Let us put Vi equal to minus 0.7 here, and then we have minus 0.7 times R2 plus R divided by R plus R2. So that gives VO, and that also will turn out to be minus 0.7 volts. So therefore there is continuity over here. Finally, let us take this case where Vi is greater than 1.7 volts. For this range, D1 conducts and D2 does not conduct, as we saw earlier. And what is VO in this case? VO is 0.7 plus 1 plus I1 R1, this equation here. And now let us obtain I1 by writing the KVL equation for this loop. So let us begin at this point. We go up first. We come across a rise of Vi, so that we write as minus Vi. Then we come across a drop, I1 times R, then 0.7, then 1, then another drop, I1 times R1. When we add all of these terms, we get 0, and that gives us this equation here. And we can solve this equation for I1. I1 turns out to be Vi minus 1.7 by R plus R1, and we can now substitute this I1 back over here and get VO. So VO finally is R1 by R plus R1 times Vi plus 1.7 times R by R plus R1. Now the slope in this region, dVO dVi, is given by this factor here. R1 is 1.5k, R is 1k, so therefore the slope turns out to be 3 by 5. Here is the VO versus Vi relationship for Vi greater than 1.7 volts, and it's a straight line with a slope equal to 3 by 5. And you can verify that there is continuity at Vi equal to 1.7 volts. Alright, so our VO versus Vi relationship is given by combining these three pieces together, and that is what we get. The SQL file for this circuit is available to you, so you can run the simulation and check out the results. The next part of our problem is to find VO as a function of time given a triangular input voltage varying from minus 5 volts to plus 5 volts with a frequency of 500 Hertz. So here is our input voltage waveform. This is the Vi axis. This is the time axis. Vi varies between minus 5 and 5 volts. And what we have shown here is one cycle. Since our frequency is 500 Hertz, the time period is 2 milliseconds. And that is what we have over here, 0 to 2 milliseconds. Here is VO versus Vi as we obtained earlier. So what we want to do now is to use these two to obtain VO as a function of time. And to do that, we will use this plot here. This plot is time versus time. So that means it is of the form y equal to x, which is a straight line with slope equal to 1 and passing through the origin, like that. And as we will see, this graph is going to help us to map Vi of t to Vo of t. Let us show that using an example. Let us consider this particular point on the Vi of t graph, and let the time here be t1, so that is given by whatever this number is, and let the Vi value be given by Vi1, so that means this number. So this point here is t1 Vi1. Now corresponding to this point, we want to find t1 Vo1 in the Vo of t graph. This is our Vo axis, and that is our time axis for the Vo of t graph, and we are looking for this point over here, which we find by this construction here. And at this point we have t equal to t1 and Vo equal to Vo1, and that corresponds to this point on the input graph. And let us see the correspondence between these two. Now this is t1, and because this graph represents t equal to t, this must also be t1, and therefore this vertical line here represents t equal to t1. Alright, so that takes care of the time part in the Vo of t graph. Let us look at the Vo part now. What is the input voltage? The input voltage is given by this number here. So this vertical line represents Vi equal to Vi1, and the intersection of this Vi equal to Vi1 line with this Vo versus Vi relationship gives us the corresponding output voltage, and we will call that Vo1. So this horizontal line represents Vo equal to Vo1. As we saw earlier, this vertical line represents t equal to t1, and therefore the intersection of these two lines gives us the required point in the Vo of t graph. This process can be repeated for other points in the Vi of t graph. For example, let us consider this point here, call it t2 Vi2. This horizontal line as well as this vertical line represent t equal to t2. This vertical line represents Vi equal to Vi2, and this horizontal line represents Vo equal to Vo2, where Vo2 is the output voltage corresponding to Vi2. And finally, the intersection of this Vo equal to Vo2 line and t equal to t2 line gives us the point that we are looking for in the Vo of t graph. And we can repeat this process for all other points in the Vi graph, and that gives us Vo of t, like that. Let us now look at some animation, and that will make this clearer. So here is a circuit that we were just looking at. The component values such as R, R1, R2 can be selected over here. For example, R can be 0.5K, 1K, 2K or 5K. R1 can be 0.01K, a very small resistance, that is 10 ohms, or 0.1K or 0.5K, 1K, 2K, 5K, or it could even be infinity. Now when we select R1 equal to infinity, what we are doing essentially is to remove this branch from the circuit, because we have an open circuit instead of R1. Similarly, R2 has the same options. VS1 can be -5 volts or -4, -3, etc. up to 5 volts, and VS2 also has those same options. Let us choose Vs2 to be 0 volts because if you recall, we did not have a voltage source over here in our example, and by making Vs2 equal to 0 volts, we are going to make this a short circuit. Let us choose R1 and R2 to be 1K each. These values are a bit different than what we had in our example, but that would not make too much difference to our VO versus VI curve. It will only change the slope values but not the breakpoints. Okay, let us now compute the VO versus VI relationship, and this is what it is. This axis is VI going from -5 to +5 volts. This axis is VO, again going from -5 to +5 volts, and that is our VO versus VI characteristic. Where are the breakpoints? One breakpoint is here, the other breakpoint is here. Between these two breakpoints, we have a straight line with a slope equal to 1 and passing through the origin as we would expect. Where is this breakpoint? This is 1 volts, this is 2 volts, and this is 1.7 volts as we had computed. What about the second breakpoint? This is 0, this is -1, and the second breakpoint is at -0.7 volts. Let us choose the triangular input option because that is what we considered in our example, and compute again. So this is our input voltage. That axis is V in and this one is time. So the input voltage is going from -5 to +5, and the period is denoted by T over here. Now this input voltage is repeated in this plot over there, the yellow one, and the red one is the output voltage as a function of time. What is this graph here? It is T versus T, that is time versus time, and as we saw in our slides, it is a straight line with a slope equal to 1 and passing through the origin. Let us now start the animation, and then we will be able to observe how this VI of t graph gets mapped into the VO of t graph here. And as we discussed, that is done using this graph of t versus t and the VO versus VI relationship. Let us start the animation. Pause. Now at this point, D1 and D2 are not conducting and therefore they appear in red. Let us continue. Pause again. At this point, note that D1 conducts and D2 does not. So therefore D1 has appeared in green color now, whereas D2 continues to be in red. Notice also that the conduction path is shown over here, and if you observe carefully, that will keep changing. Continue. So no diode is conducting now. Now D2 has started conducting. Also the current path has changed. And that is the end of the simulation. In summary, we looked at a circuit with two diodes, figured out conditions for each diode to be conducting, and then looked at the implications for the VO versus VI relationship. We then used the VO versus VI relationship to map a given VI of t to VO of t. We have also used animation to illustrate this mapping process. That is all for now. See you next time.